Designers lack insight into how robust different design choices are to variations in category numbers. Our results show that both number of categories and color palette notably impact people's perception of categorical data in Scatterplots. We examined existing palette design heuristics in light of our results to help designers make robust color choices. Hello everyone, my name is Qing Zhen. Today I will talk about our paper, Measuring Categorical Perception in Color-Coded Scatterplots. This work is in collaboration with Gulan Quadri, Zhou Wang, and Daniel Safar from the University of North Carolina at Chapel Hill. We know that scatterplots commonly use color to encode categorical data. However, as datasets increase in size and complexity, the efficiency of these channels may vary. In other words, when the number of categories increases, people's abilities to analyze patterns across categories may degrade. Moreover, let's say we have a categorical dataset. How do we make choices between different color encodings for multi-class scatterplots? Existing studies provide guidance for supporting a range of tasks in general scatterplots, such as cluster estimation and tuning across channels such as color differences. However, little attention has been paid to design choices for rendering complex multi-class scatterplots and how such design choices may change as the number of categories increases. Available design guidance for effectively supporting categorical tasks is largely heuristic rather than empirical, which raises questions as to robustness and precision of this guidance across a range of scenarios. This is the outline of our talk. We're first doing the introduction of our research question and experiments. Then second part, we will see the results. And finally, we will do the discussion on our findings. Let's go into our introduction. So our target research question is how robust different palette designs are to increasing numbers of categories. We conducted a crowdsourced study to measure how the number of categories and choice of color encodings using multi-class scatterplots influence the viewer's abilities to analyze data across classes. Participants were asked to estimate mean values in a series of multi-class scatterplots with varying number of categories, data sizes, which is the number of points, and color palettes drawn from popular visualization tools. Our results shows that the number of categories and choices of color palettes significantly impact people's perceptions of categorical data in scatterplots, and that the judgments becomes harder as the number of categories grows. But there are some caveats. We deconstructed our results with respect to common parameters of color encodings to find potential cues for robust palette design. So, what are the key factors for effective color palette design? Our results characterize the effect of the number of categories and color palettes in perception of multi-class scatterplots. Our findings challenge current guidelines on multi-class scatterplot design, and we present an exploratory analysis of key factors for effective color palette design. For experiment design, we have 4 factors. We tune our dataset parameters in a series of 3 extensive pilot studies. The first factor is category number. We have from 2 categories up to 10 categories in a single scatterplot. Second is the color palette. Choosing a proper categorical color palette for visualizing categorical data is a crucial task. We selected professionally designed color palettes from a range of sources. Each color palette has support at least 10 categories. Third is the hardness level. We define the hardness level as the distance between the 2 highest y-means. We also restrain the lowest y-mean at a certain range to prevent subsequent means from drifting too far apart and artificially simplifying the task. Finally, the point number represents the number of points in each category. In each scatterplot, every category shares the same number of points, ranged from 10 to 20. Here are some examples of our stimuli. We generated each scatterplot as a 400 by 400 pixel graph using D3. We use multivariate normal distribution to generate positional data with the given mean and covariance. These 3 plots are showing the scatterplots with different numbers of categories. Here are the examples showing how the scatterplots look with different hardness level. As we mentioned earlier, that the hardness level delta is the distance between the two highest y means. So as the delta number is smaller, the test is considered harder. Here is our experiment interface. We employ a relative mean judgment task. We ask participants to estimate the category with the highest average y value. We use this test as it requires participants to first find data points of different categories and then estimate statistical values of overall points in that category. There are 45 tasks for each participant. Each task has a time limit of 15 seconds. Let's get into the result part. We recruited 95 participants from the US and Canada through Amazon Mechanical Turk. We excluded 4 participants who failed to answer at least 2 out of 3 engagement checks. These 3 plots are engagement checks. That leads to our final number of 91 participants. Let's see the results. The first column is showing the accuracy, and the second column is showing the average response time to a single task. The first row shows the results broken down by category number. We can see that people were both less accurate and slower with higher numbers of categories. The accuracy rate decreases based on the number of categories, from 96.4% to 86.6%, with an overall descending trend as the number of categories increases. Similar to the hardness level, as the test becomes harder, accuracy drops and the response time escalates. However, both accuracy and time do not systematically vary with regard to the number of points. Our analysis reveals a significant effect of both the category number and color palettes. The robustness varies depends on the color palettes. SFSO parties and color brewer 3 achieve the highest average accuracy rate in all data, whereas Photomuted and Stata-S1 exhibited the worst overall performance, with an 11.3 accuracy difference on average between SFSO parties and Stata-S1. Here we are showing the examples of scatterplots with the number of categories equal to 3. The mean accuracy for Stata-S1 when number of categories equals to 3 is 82%, and for SFSO parties is 97%. Let's see how it looks when having higher number of categories. When scatterplots with 8 categories, they have mean accuracy of 56% and 81% respectively. To better analyze the impact of specific color palettes, we analyzed the results using 8 color metrics associated with palette design to explore the relationship between performance and common design parameters, like perceptual distance, name differences, name uniqueness, and the magnitude and variances of different dimensions in CICLCH. These 2 plots show the palette color brewer 3 with a high L magnitude and one palette Stata-S2 with a low L magnitude. These 2 plots shows Tableau Tab 10 palettes which has a larger perceptual distance versus Stata-S1 with smaller perceptual distance. The last 2 show palette Photomuted which has a higher L variance, whereas Color Pastel which has a lower L variance. We found that larger L magnitude, which is lighter colors, and larger perception distance both led to a better judgment accuracy, whereas palettes with less lightness variance had better performance. The discussion. We measure the impact of the number of categories and choice of color palettes on people's perceptions of multi-class scatterplots. We find that people are less accurate at assessing category means as the number of categories increases. However, certain palettes may be more robust to variations in category number. Contrary to past heuristics, we found that performance remained relatively high even for more than 7 categories. We hypothesized that people may simply be better at this test than they expect, while the task may feel significantly more difficult as the number of categories increases. Our visual system may be more robust than expected in working with complex categorical data. Designers can use our results to directly choose the optimal palette from our tested set of palettes given the number of categories in their data. Our results also provide preliminary guidance for palette selection. In conclusion, we measure how different color palettes impact people's abilities to distinguish classes and assess mean values on multi-class scatterplots. We believe that our findings have the potential to support a variety of other visualization types and low-level tasks that combine continuous and categorical data. Please check out our paper to find more details. This is the end of the talk. Thank you.